Hi, everybody. It's Professor Mitchell. Today, we're going to talk about section 7.7 on hyperbolic functions. So I always enjoy introducing this section by giving you a fun fact. So first of all, recall that a function f is even if f at opposite x is equal to f of x for all x in the domain of f. And f is an odd function if f at opposite x is equal to the opposite of f of x for all x in the domain of f. So the fun fact is that every function can be written as the sum of an even function and an odd function in exactly one way. And I'm going to try to convince you of part of this. I'm going to try to convince you that every function can be written as the sum of an even function and an odd function. This doesn't show that this is the only way to do it. So it turns out that f of x can be written as e of x plus o of x, where e of x is equal to f of x plus f at opposite x all over 2. And O of x is equal to f of x minus f at opposite x over 2. So what you might want to take a moment and convince yourself of is that this e of x is in fact an even function and O of x is an odd function. And that's pretty easy to do. I'll leave that for you. So if the function in question is f of x equals e to the x, then e of x would be e to the x plus e to the negative x over 2. And O of x would be e to the x minus e to the negative x over 2. And it turns out that these particular functions are interesting in their own right, so they have special names. Those are called the hyperbolic sine and hyperbolic cosine of x. The hyperbolic sine of x, sometimes called sinh x, is e to the x minus e to the negative x over 2. So this is sort of the odd component of e to the x. And the hyperbolic cosine of x, also known as cosh x, is e to the x plus e to the negative x over 2. And then you can define the other hyperbolic functions. These might remind you of some functions that you've seen before. Notice that these are defined, these other 4 functions are defined exactly the same way that the other 4 trig functions are defined. So the hyperbolic tangent of x, I don't know if it's common to call that tanh. I think it is actually. Is sinh x over cosh x, just like the tangent of x is sine x over cosine x. And then remember how sinh x and cosh x are defined. So that expression would simplify down to e to the x minus e to the negative x divided by e to the x plus e to the negative x. Then you have the hyperbolic cotangent of x. And again, I'm not sure if the nickname coth is standard. You can see how that's defined. I am pretty sure that the hyperbolic cosecant does not have a nickname. I'm not sure how you would pronounce it, if it would be cosich x, right? I probably wouldn't call it that. And then the hyperbolic secant of x. The graphs of the hyperbolic functions look like what you see here. So you have the hyperbolic sine, the hyperbolic cosine, and they're showing you how this, in this illustration, how those are constructed from the graphs of y equals e to the x over 2 and y equals negative e to the negative x over 2 in the case of the hyperbolic sine. Then you have hyperbolic tangent and hyperbolic cotangent on the same coordinate system up there in the upper right corner. And then down at the bottom, you have the hyperbolic secant and the hyperbolic cosecant. Now, when I was reviewing this presentation today, I looked at the graph of hyperbolic cosine, and it reminded me of a meme that I saw on Facebook just yesterday. So I had to go and grab that for you. This is from a page called Math with Bad Drawings. This is a Facebook page. And the thing that I want to point out is really the top row. So it turns out that a hanging chain looks like a parabola, but what it really is called a catenary. And catenary has the equation y equals a times cosh of x over a. All right. And then the rest of this meme is pretty cute. An orbit might look like a circle, but it's actually an ellipse. And then it looks like we're procrastinating by reading memes, but what we're really doing is, okay, moving on. All right, some identities for hyperbolic functions. These might remind you of some identities for trigonometric functions. I do want to point out that there are a few differences. For example, if we replaced all of these with their corresponding trig functions, the identity with the trig functions, this first one would be cosine squared x plus sine squared x equals 1. This one would be the same. This one would turn into cosine 2x equals cosine squared x minus sine squared x. This one would stay the same. I believe this one, the two terms here would just flip around. And then I don't know if I've ever had the opportunity to say this to you, but the Pythagorean identities that relate secant to tangent and cosecant to cotangent, even after all these years that I've been doing math, I do not trust myself to remember those correctly. And so every time I need one of those, I literally derive it from sine squared x plus cosine squared x equals 1. So I'm pretty confident that these two identities here, if you change them to their corresponding trig functions, you do have to change a sign, S-I-G-N, somewhere. So the point is that some of these stay exactly the same and some of them are just a little different. I wanted to take a moment to convince you of at least one of these identities. Should be pretty easy to do any of them. So let me bring up the tablet. So I'm going to try to convince you of the first identity, cosh squared x minus sinh squared x equals 1. So as you hopefully learned in your trig and pre-calc classes, the correct way to verify an identity is to start with the more complicated side, which is definitely the left side in this case. And then just play with it until you're able to turn it into the thing that you want. So I am going to replace cosh x and sinh x with their definitions. Remember that cosh x is e to the x plus e to the negative x over 2. And sinh x is e to the x minus e to the negative x over 2. All right, so when we multiply those things out, this thing is going to end up being over 4. And then I'm going to make like I'm squaring a binomial. So e to the x squared is e to the 2x. And then e to the x times e to the negative x is 1, right? And you'd have 2 of those. So this would be a 2. And then e to the negative x times e to the negative x is e to the negative 2x. If I lost you there, you might want to pause the video and then you can just FOIL e to the x plus e to the negative x times e to the x plus e to the negative x. And you should be able to convince yourself that that's correct. Then I'll do the same thing over here. E to the x times e to the x is e to the 2x. E to the x times negative e to the negative x is negative 1. And I have 2 of those, so that would be minus 2. And then negative e to the negative x times itself is e to the negative 2x. All right, so then These fractions both have denominator 4, so you can combine them together. Notice that there is a minus sitting in front of this fraction, which means that this minus sign has to be distributed. And what ends up happening, hopefully you can see this, is that the e to the 2x and the minus e to the 2x cancel. The e to the negative 2x and the minus e to the negative 2x cancel, because remember this became a minus. However, this negative 2 right here became plus 2. So what we're left with is 2 over 4 plus 2 over 4, which is 4 over 4, which is 1. And that's exactly what I wanted to show that it was. All right, so if you need to verify any of these identities, you just do it using the definition of the appropriate hyperbolic function. All right, so back to the presentation. All right, and now we get into some examples. In this first problem, we're going to use the definitions and the identity cosh squared x minus sinh squared x equals 1 to find the values of the remaining 5 hyperbolic functions, given that sinh x is equal to 4/3. And then we're going to rewrite this expression in terms of exponentials and simplify. The expression is sinh of 2 natural log x. So now I'll go back to the tablet and we'll look at those 2 examples. All right, so given that sinh x is equal to 4/3, we can find cosh x using the identity cosh squared x minus sinh squared x equals 1. All right, so substituting 4/3 for sinh x, we would get cosh squared x is equal to 4/3 squared. I'm sorry, cosh squared x minus 4/3 squared equals 1, which means cosh squared x minus 16/9 equals 1. And then if we add 16/9 to both sides, we get that cosh squared x is equal to 25/9, which means cosh x is either the positive or negative square root of 25/9. So cosh x is either 5/3 or negative 5/3. Now, when you did this kind of problem with trig functions, they always gave you some information about what quadrant the corresponding angle was in, and that's how you figured out the sign SIGN of the missing trig function, in this case cosine. But hyperbolic functions have nothing to do with angles. They have everything to do with this definition, and you can actually use this definition to figure out whether this thing is positive or negative. Remember that cosh x is e to the x plus e to the negative x over 2. So think about, when is that thing positive and when is it negative? Well, it's actually never negative, right? E to the x is always positive, and therefore e to the opposite x is also always positive. This thing is always positive. It is not possible for cosh x to be negative 5/3. Cosh x has to be 5/3. And that's it for that problem. All right, and then we have this one, sinh of 2 natural log x. So remember that sinh x is equal to e to the x minus e to the opposite x all over 2. And I left some blanks there because those x's are going to get replaced with what's actually in this function, which is 2 natural log x. Okay, so now we want to try to simplify this thing. And the way that I'm going to simplify it is I'm going to use my power property of logarithms. You know how much I love that thing. To take this 2 and go, and take this -2 and go. So what we find is that this is e to the natural log x squared. And this other thing is e to the natural log x to the -2. And that's all over 2. E to the natural log x squared is just x squared. E to the natural log x to the -2 is just x to the -2. Right? I don't know about you, but I was brainwashed in Math C not to leave any answers with negative exponents. So I am going to multiply the top and the bottom of this fraction by x squared. And that is going to give me x to the 4th minus 1 all over 2x squared. All right. So there's a couple of examples with basic hyperbolic functions, no calculus involved. All right. So now let's do some calculus. We're going to use the definitions of our hyperbolic functions to find the derivatives of sinh x and cosh x. It might be kind of fun to guess. What do you think those derivatives are going to turn out to be? And now let's see. So we'll start with the derivative of sinh x, and we'll use the definition. So remember that sinh x is e to the x minus e to the opposite x over 2. So I think the first thing I'll do is pull out that 1/2, put that out front. Hopefully you weren't thinking about using the quotient rule on that, by the way. I mean, you can, it just, makes it a little overly complicated. All right, so now we'll take the derivative of e to the x, which is just e to the x. And then we will subtract the derivative of e to the opposite x, which is e to the opposite x times the derivative of opposite x, which is -1. So that comes out to e to the x plus e to the opposite x all over 2. And have we ever seen that expression before? Well, yes, e to the x plus e to the opposite x over 2 is exactly how we defined cosh x. So if you guessed that the derivative of sinh x was going to be cosh x, you were absolutely right. So then I bet the derivative of cosh x is going to be negative sinh x, right? Because the derivative of cosine x is negative sine x. Well, let's see. The derivative of e to the x plus e to the opposite x over 2. We'll pull out the 1/2. The derivative of e to the x is e to the x. The derivative of e to the opposite x is e to the opposite x times -1. That comes out to e to the x minus e to the opposite x over 2. And is that negative sinh x? Well, no, it's actually just sinh x, right? And now that I think about it, that's not a big surprise, right? Because when we were looking at those identities, we noted that some of the signs, SIGN, were different in the hyperbolic identities than they were in the corresponding trig identities. So I guess it's not a big surprise that this SIGN is also different. All right, so there you have it. The derivative of sinh x is cosh x, and the derivative of cosh x is sinh x. So now let's look at the derivatives of our other hyperbolic functions, and I'm not going to prove these to you. They're easy enough to prove yourself. The derivative of tanh, notice I'm giving you the chain rule versions. The derivative of tanh u with respect to x is hyperbolic secant squared u times du dx. So that one's exactly like the corresponding trig one. This is exactly like the corresponding trig one. And the bottom one reminds me a lot of the derivative of cosecant u. So there are exactly two of these here where the SIGN is different. And that's this one and this one. When you take the derivative of secant u, you get secant u tangent u with no negative. When you differentiate cosine u, you get negative sine u. So those two, the SIGN is different. But on the other four, it's exactly the same. All right. So now, and so of course, each derivative formula has a corresponding integration formula. All right, so now we'll look at some calculus examples, and then this will be the end of section 7.7. Go back to the tablet one last time. And here we go. All right, in example 1a, we're looking for the derivative of y equals t squared times the hyperbolic tangent of 1 over t. So of course, that's a product rule problem. So we're going to have dy dt is equal to the first times the derivative of the second plus the derivative of the first times the second. All right. So now we're going to have a little bit of chain rule. The derivative of tanh 1 over t is hyperbolic secant squared 1 over t, but then we have to multiply by the derivative of 1 over t. So that's from the chain rule. So maybe I'll just write that down at this point. This is all chain rule. And then the second term is very simple, right? The derivative of t squared is 2t. And then we're going to leave this one alone. Okay, so what is the derivative of 1 over t? Is it natural log t? No, that's going in the wrong direction. You actually learned the derivative of 1 over t in Calc 1. The derivative of 1 over t, that's a power rule problem. Sorry, you think of it as t to the negative 1, and then the derivative is negative 1t to the negative 2, which is negative 1 over t squared. And that derivative comes up frequently enough that you should be able to just call it up without having to think about the power rule, if you can. So what we're left with here is t squared hyperbolic secant squared 1 over t times negative 1 over t squared. And I think you can see the pretty thing that's going to happen there. This one I'm going to leave alone. And then what I can do in the first term is get rid of the t squareds, right? Goodbye, goodbye. All right, so final answer. I think I'll write the second term first. I don't like to start expressions with a negative sign if I don't have to. So it's going to be 2t hyperbolic tangent 1 over t minus hyperbolic secant squared 1 over t. And that's it, right? All right, and then the other derivative example is this one, y equals natural log sinh v minus 1/2 coth squared v. So this is one of those, it's an ugly function and it's asking for the derivative. So I wouldn't be surprised if the derivative comes out to something nice and pretty. Let's see. So in this problem, we're looking for dy dv. Okay, so first we have a chain rule. The derivative of natural log sinh v is going to be 1 over sinh v times the derivative of sinh v, which is cosh v. Okay, and then over here next door, we have a chain rule problem. We're going to leave the 1/2 just sitting where it is. And then the derivative of coth squared v, the outside function, is the squaring function. So we're going to apply power rule to that first. It's going to be 2 coth v. And then we have to multiply by the derivative of coth v. And that one works exactly the same way as cotangent. So that derivative is going to be negative hyperbolic cosecant squared v, right? Okay, so what do we have here? We have cosh v over sinh v, which we can write as coth v. Then we have 1/2 times 2. And we have 2 minuses here, so we might as well make that plus coth v times hyperbolic cosecant squared v. Now, I have a feeling that we might be able to simplify this using an identity. So let me just, actually, I'm going to pause you for just a second. Yes, I see an identity here that I think we can use. Look at that bottom identity. Coth squared x equals 1 plus hyperbolic cosecant squared x. So how am I going to use that? Well, I am going to take the expression that I have, which is coth v plus coth v times hyperbolic cosecant squared v. I'm going to factor out coth v, which leaves me 1 plus hyperbolic cosecant squared v. And then the identity that we were just looking at here says that that thing is equal to coth squared v. All right. See, what did I tell you? Ugly function, you take its derivative. A lot of times it's rigged to come out to have a nice, pretty answer. So I think the pretty answer they were looking for here is coth cubed v. All right, and that brings us to our integration problems, starting with the integral of hyperbolic cosecant natural log t, coth natural log t over t, dt. This looks like a classic substitution problem. So we're going to let u equal natural log t, which is going to make du be 1 over t dt. Oh, which is exactly the thing I needed, right? Here's my 1 over t dt. So that's going to get replaced with du. So this integral in terms of u is just going to be integral hyperbolic cosecant u coth u du. And that integral is just like cosecant u cotangent u du, which is negative cosecant u. This one is going to be negative hyperbolic cosecant u. But of course, it's not about u, it's about t. So negative hyperbolic cosecant natural log t plus C. All right, and then finally, we have a definite integral from 0 to natural log 10, 4 times sinh squared x over 2 dx. So what we're going to do with that sinh squared is the same thing we do with sine squared. We're going to use an identity. And let me just tell you what that identity is. We are going to use the identity sinh squared u equals cosh 2u minus 1 over 2. Remember, that was one of the identities we were looking at on the other slide. It was slightly different from the corresponding trig identity. All right, so what that's going to do to this integral, why don't we put this 4 out here? It's going to be integral 0 to natural log 10. And we're going to have cosh of 2 times x over 2. X over 2 is playing the role of u, minus 1 all over 2, right? Okay, so now I'm going to bring out that over 2, which is really bringing out a 1/2. So now this is going to be 2 integral 0 to natural log 10 of cosh x minus 1. All right, and I think we can do that integration pretty easily. The integral of cosh x is sinh x. The integral of 1 is x. We're going to plug in natural log 10 and plug in 0. And that is going to give us 2 times sinh natural log 10 minus natural log 10, right? Minus sinh 0 minus 0. Okay, so here's one reason why I gave you that sinh of 2 natural log x problem earlier. Here, why don't we do this part down at the bottom? So sinh natural log 10 is going to be e to the natural log 10 minus e to the negative natural log 10 all over 2. So this is going to come out to 10 minus 10 to the negative 1 over 2. And if I multiply the top and the bottom by 10, that is going to give me 100 minus 1 over 20. So it looks like 99 over 20. So we have 2 times 99 over 20 minus natural log 10. And then sinh 0, I think that's a little simpler. That's just e to the 0 minus e to the negative 0 over 2. Well, e to the 0 and e to the negative 0 are both 1, so that comes out to 0. So guess what? We don't even have to worry about that part. Okay, well, there it is. I don't think distributing that 2 is going to make it look a whole lot nicer. Well, we can make this 99 over 10 minus 2 natural log 10. All right, and that's going to do it for section 7.7. We'll see you next time.